Hello there, Mr. Sutton here, bringing you the Algebra 2 6-3 lesson on logarithms and logarithmic functions. In this one, we will be converting between exponential and logarithmic form, and we will be evaluating some logarithmic expressions. So you might be wondering at this point, what is this whole log thing? You might have heard about it before, but the name itself isn't very descriptive of what it is and actually does. So if we have the log base b of x, that's how I would say that. This is the number, the power, that I have to raise b to in order to get this x expression inside. So every log has a base, and it also has an input. The log of a base and an input is just what you have to raise the base to get the input. So as an example, we know that 2 to the 5th equals 32. Therefore, we can kind of turn this around and say the log base 2 of 32 equals 5, because 2 to the 5th equals 32. 5 is the number I have to raise 2 to in order to get 32. So these two different forms actually have names. This first one is called the exponential form, and this other one with a log is, not surprisingly, called the logarithmic form. And we can go back and forth between these two forms if we kind of understand where things are going. So the general exponential form, we can write this as b, a base, to some n, some exponent, equals x, which in this case, we have 2, 5, and 32. But we can also put that in logarithmic form. We can write log base b of this output here, x, equals this original exponent, equals n. So if you're going back and forth between these two forms, really the base is staying the same. The base of the log is the base of the exponential. It's just the x and the n, kind of the input and the output, that are trading places. Now there's some special forms of, there's some special logarithms out there. Normally the log will say what the base is in this little subscript right next to it, but there are two notable exceptions. If you just see log without any subscript at all, that really means log base 10, which is called the common log. And I think it's common because our number system is base 10, so this is kind of the one that they started with. The other special log out there isn't even spelled with an log, it's actually spelled with an ln. This ln is really just log base e. And you might wonder, well, what is going on with the ln? This is, I guess, log natural, because e is the natural base. That's probably where it comes from. So now that we've talked a little bit about what log represents, we're going to do a few kind of entry-level sort of problems with logarithms. These are going to be rewriting equations in exponential form if it starts in log form, or in log form if it starts in exponential form. By itself, these things aren't super useful, but they're useful for doing other things, such as finding inverses, solving equations with both types of things going on. So this is kind of like the wax on, wax off, polishing the car to get better at karate from the Karate Kid sort of thing. So just a little tip, and then I'll have you try these on your own here. The base, remember, in both of the forms, exponential and logarithmic, is actually going to be the same. It's just the two other numbers, the input and the output numbers, are switching. So with that in mind, pause the video and see if you can rewrite these first two equations here in exponential form. All right, so our first one here, we have a base of 2, so this is going to be 2 to something equals something. And we switch the input and the output. So we're going to have 2 to the 6 equals 64. And the nice thing about doing this with numbers is you can kind of look at it and say, hey, does that actually make sense? Is 2 to the 6th power actually 64? And it sure is. On to the next one here. We have a base of 1/4. So this is saying 1/4 to the output here, -1, equals 4. And is that true? Well, yeah, this is reciprocal, turns your fraction upside down, and that would give us a 4. All right, so that's the basic idea going to exponential form. Now let's see if you can reverse directions and put these two exponential equations in logarithmic form using kind of the same idea. Pause the video and give this one a shot. Let's see how you did. So for this first one, we have a base of 10, so that's going to be the base of the log. We're going to have log base 10, which we don't actually have to write because it's the common log. So we have log base 10 and then switch the input and output. So log base 10 of 0.1 equals -1. And that is also true. 10 to the -1 equals 0.1. Now we'll do this other one here. We have base 8. So log base 8 of 4 equals 2/3. 4 is what you get if you raise 8 to the 2/3 power. You would cube root the 8 to get a 2 and square that to get a 4. So on those last several problems where we were changing forms, we talked constantly about swapping the input and the output in order to make that change. Well, swapping input and output, you might remember from before, is kind of the definition of an inverse. So it's only a matter of time before we come to this idea that exponentials and logarithmic expressions are actually inverse functions of each other. So in order to find the inverse, that means we basically just need to change forms at some point. Now this is going to be necessary for other reasons as well. Remember, when you're finding an inverse, you're swapping the x and the y and then solving for the y value. Once you do that, you're going to notice you have a y stuck either in an exponential function or in a logarithmic function. To isolate a variable that's inside one of those two types of functions, rewriting the equation in whatever the inverse form was is going to actually get that variable out of whatever function you were trying to bust it out of. So with that in mind, pause the video and see if you can find the inverses of these functions. All right, so for part A, we're going to swap x and y. So I'm going to write x equals 6 to the y. And to get the inverse, I just have to get y isolated out of this exponential. So I'm going to change this into logarithmic form. The base is 6, so I'm going to have log base 6 and then swap the input and the output. Log base 6 of x equals y. Now, since y is really going to end up being f inverse, I can write f inverse equals log base 6 of x. All right, and you can actually, well, I was going to say test these things out, but to do that you'd need to be able to evaluate things. So maybe we'll save that for a little bit later on. Going on to this next one, we swap the x and y, so we have x equals ln of y plus 3. And again, to get rid of this ln, this is really just log base e. We have to put this in that other exponential form that we have over here. So I'm going to keep my base, which is base e. I'm going to say e to the, and then swap the exponent and swap the input and the output here. So e to the x equals y plus 3, just changing this into exponential form. And then just one more step, subtracting this 3, we have f inverse equals e to the x minus 3. So this is the end of part 1 of this lesson. It's all about changing forms in this first part. In part 2, we're going to come back and evaluate some logs using both a calculator and no calculator, and we'll also do some simplifying. Until then, Mr. Sutton, temporarily signing off. All right, welcome back. You're joining us for part 2 of this lesson on logarithms and logarithmic functions. In this one, we're going to start by evaluating a bunch of logarithms. Now, keep in mind on all of these, you're basically just asking, what do we need to raise the base to in order to get the input inside the log function? So remember, you're looking for an exponent that turns the base into the input. So one trick you can do, one kind of mental strategy in order to achieve this, is to try rewriting your input as the base to some power. So with that in mind, pause the video and see how many of these you can get. All right, let's go through these now one at a time. So for the first one, I'm asking, what do I need to raise 4 to get 64? Well, 64 is 4 to the 3rd power. Therefore, log base 4 of 64 would equal 3. And then on to this next one, we have a log base 5 and a 0.2. Those don't look like they have anything in common until we recognize that 0.2, if we express that as a fraction, which is usually good to do in these situations, is really 1 over 5. And 1 over 5 is really 5 to the -1. That's just the reciprocal of 5. So this means then that log base 5 of 0.2 is this exponent of -1. Moving on to part C here, we have 1/5 for the base and 1/25 for the input. Now this one is a little bit trickier, except if you can't get the exact base right away, if you can at least turn the input into something that has the base, that might help. So I don't know what power of 1/5 125 is, but I know 125 is 5 to the third power. That might be useful. And let's see here. We saw over here that 5 and 1/5 have this reciprocal relationship. So I could make this 1/5 to the -3 and it would be the same, it would be an equivalent expression here. Well, this means that log base 1/5 of 125 is actually just this exponent of -3. If I raise 1/5 to the -3rd power, the reciprocal would give me 5, and then cubing 5 would give me 125. So -3 for that one. And then finally, this last one is a little bit tricky. A lot of people look at this and they're like, oh, 6 squared is 36, therefore this is going to be 2. But you've got it kind of backwards if you did it that way. We're asking, what do I have to raise 36 to in order to get 6? But this squaring idea isn't too far from where we need to be, because 6 is the square root of 36. And we know that square root, if we were to express that as an exponent, we can use powers instead of radicals, right? This is really the 1/2 power. So because 6 is really 36 to the 1/2 power, the square root of 36, that means log base 36 of 6 is just 1/2. For this next set of problems, we're going to be evaluating these logarithms using technology, because sometimes it's just impossible to figure out without a calculator what I have to raise some random number to in order to get another number, especially if that other number is not a perfect power of the first number. So how can we use technology? Well, the good news is that scientific calculators, including Desmos, can do log, base 10, and ln. The bad news is that they can only do log, base 10, and ln. At least with direct commands and buttons. There is a little bit of a workaround, but it's not as intuitive as just if you have those two situations. Now, graphing calculators can do other bases. I know the TI-83 has a function built in, and Desmos also has one where you can do any base. You just need to type in log and then do an underscore, and it'll put you into subscript mode, allowing you to specify any other base. So if you're able to access a graphing calculator, you can directly find something like part C here. There is a workaround, though, if you only have access to a scientific calculator, which, depending on the exam you're taking, you might only have access to Desmos Scientific. So in that situation, you can do any base on a scientific calculator by using this change of base formula. The change of base formula says that if you're trying to find log base b of x, you just need to do log of x divided by log of b. And notice that this is just log base 10, like regular common log, which any calculator can do. So just do log of the input divided by log of the base, and that will give you this expression. So with all that in mind, pause the video and just practice finding logs with technology on these three examples. And for part C, I would recommend you try it with both methods, both the grapher Desmos log underscore and the change of base formula, just to see that they do give you the same thing. All right, let's see how that went for you. So let me show you Desmos for log of 8. So we just type in literally just log, L-O-G, 8, and we get a number, 0.903 and some change. So there it is. Now, if you're questioning whether this is the true answer, you can always check it by raising what you just got, raising the base to whatever you just got. So let's do 10 exponent 0.903, and it's not going to be exact because we're rounding off, but we can see it gives us pretty close to 8. Now for this next one, ln of 0.3. For this one, we just type in ln 0.3. And that tells us what I have to raise e to get 0.3, in this case negative 1.204. And then finally, doing log base 7 of 43, we'll do the change of base formula first. And let me just move my calculator so I can see. So we're going to have, let me make a fraction, log of 43 divided by log of 7. And that supposedly is about 1.933. So there we go, change of base. But let me go to Desmos graphing calculator now, and I'll have to expand this to get a little more room on my graphing calculator. Desmos graphing. Let's do log underscore, and now I can specify the base 7 there, and then arrow out of that and put in a 43. And we get the same answer we got using the change of base formula. At this point, we're going to be doing some simplifying of logarithms. Now, when you evaluate a logarithm, that is kind of simplifying, but this is sort of a different take on all that. So the key concept we're going to be using on these problems down here is the idea which we kind of saw when we were evaluating logs and rewriting in terms of the base, that logarithmic and exponential functions that have the same base kind of cancel each other out when they interact directly. For example, when you have a log of a base and the input is that same base raised to an exponent, well, let's reason out what's happening here. I'm asking, what do I have to raise this b to in order to get b to the x? Well, I have to raise b to the x in order to get b to the x. So this answer is just x. When you have a log base and a same exponent base, those essentially cancel and you just get whatever the input of the exponent was. Now going the other direction, let's say that we have a base, raised to a log that has the same base with an x inside. Remember, logs are just exponents. So this log base b of x is the thing I need to raise b to in order to get x. Well, if I raise b to the number I have to raise b to in order to get x, if I raise b to that power, I get x. So basically, when you have a base to a log with the same base, those cancel each other out as well, and you get whatever was inside the logarithm. So using that concept, see if you can figure out how to untangle these two problems down here. All right, let's see how this went. So we have log base 5, and we don't have a 5 to the x. That would be too easy. We have a 25 to the x. But we could probably rewrite this 25 in a way that gives us the same base, right? 25 is really just 5 squared. And if I have 5 squared to the x, well, we can just multiply those exponents, and this is just going to be 5 to the 2x. Now we basically have a log base b of b sort of situation like in this rule. So in this case, remember, the log and the exponent base cancel, and you just get the exponent, which in this case is 2x. Now taking a look at this other problem, e to the ln of 4, the key on this one is recognizing that ln is really log base e. So the e and the log base e, those are going to cancel, and that just gives me 4. So if you are taking the CP non-honors version of the course, this is the end of the lesson for you. Feel free to log off the video and try out some more problems based on evaluating and simplifying logarithms. If you're doing the honors version, we've got a cool word problem waiting for you. See you there. All right, so here is our honors level final boss battle here. There's lots of places that logarithms actually do get used in a real life setting in the sciences. This is one of the examples. So pH is on a logarithmic scale. And the pH value for a substance measures how acidic or alkaline or basic the substance is, and it's given by this formula. It's basically just negative log of the concentration of your hydrogen ions. And this is measured in moles per liter, that concentration. So they want us to find the pH of vinegar, which they're telling us has an ion concentration of 10 to the negative 3 moles per liter. So using this formula, see if you can figure out the pH scale rating. All right, so just plugging in the 10 to the negative 3 in for this H+. We're taking the log of 10 to the negative 3rd power. Now remember, before you reach for that calculator, log with no number written is really log base 10. So I'm asking, what do I have to raise 10 to in order to get 10 to the negative 3? Well, I have to raise 10 to the negative 3 in order to get 10 to the negative 3. So that just cancels out because it's the same log and base. So this is, we still have this negative out here. So we have a negative, and then the result of this log was negative 3. Negative negative is positive. So we see here that vinegar has a pH scale rating of 3. So this is one place that logs get used. They also get used in the how loud something is, loudness, the decibel scale. And another popular use is the Richter scale for measuring earthquake strength. And I'm going to leave you with that. Until next time, this is Mr. Sutton logging off.